We can just start. Should I start? Anyway, so first, are there any questions or any particular topic you would like me to cover? I'm not quite sure exactly what I'm supposed to do. I mean, I have some ideas on other things, like related things I can talk more about in some detail. But any specific questions on my first two lectures? So I guess what I covered was, the first lecture was relatively elementary. It was just Hartree-Fock theory of antiferromagnetism. Just studying in detail how the Hartree-Fock theory changed the Fermi, how the antiferromagnetism changed the Fermi surface. And then we did sort of first the lowest order fluctuations, which led to pairing and attractive interaction between the fermions and D-wave-like superconductivity. And in the next lecture, I started to get more exotic, where I started talking about introducing a Z2 gauge field and how that can give you somewhat more complicated, what we call topologically ordered phases, which have Fermi surfaces of not quite the right volume. Okay. So what I thought I would do, well, I can keep going for a long time since I have lecture notes from a whole year course that I've given, so I can talk about lots of things. But what I thought I'd do is just say a bit more about gauge theories, because I probably, for condensed matter physicists, that's totally unfamiliar, just as gauge theories are, on their own. We first learned about gauge theory using Maxwell's theory, which has a photon, and then photon leads to Coulomb interactions and light waves and so on. Then we learn about QCD. You hear about it anyway. I don't know how many of you take a course on QCD. You say it's a generalization of the photon, where the U1 gauge group becomes the SU3 gauge group. And then there's this new phenomenon called confinement, and then which nobody really understands, and things become really complicated. Okay, so that's what I had heard about gauge theories, 15, 20 years ago. But there are actually much simpler gauge theories around, which was studied also in the 70s and 80s in particle physics, which are discrete gauge theories, where instead of having the U1 gauge group of electromagnetism, you just have a very discrete gauge group. It's not a circle. It could be as simple as an Ising variable. So that's the Z2 gauge theory, the simplest gauge theory. And this gauge theory, as I'll try to review, has basically the same phenomena of QCD or U1 electromagnetism, but also a lot of other richness. In the same model, you can have both the analog of electromagnetism, which is free charges, and the analog of confinement, where the charges are confined. And you don't ever have to worry about renormalization and cutoffs and beta functions and horrible things like that that you first learn about when you hear about QCD. You hear about very complicated things like asymptotic freedom and beta functions flowing to strong coupling, and that's confinement. And you think that's confinement. Well, okay, it is, but you don't need any of that to understand these phenomena. And so the basic theory which came up in my discussion was this Ising gauge theory. Well, let me just write down a Hamiltonian in 2 dimensions. This is what you'd call a pure gauge theory, which was, keep the same notation, minus G sum on every bond of mu x ij minus k sum over every plaquette of product around the plaquette of mu z ij. Okay, so that's the Hamiltonian. And let's define it on a square lattice, so in 2 dimensions. And so on every link of the square lattice, there's a mu x and a mu z. And these are operators that are Pauli matrices. So what that means is that on a given link, mu x squared is always 1. So mu x whole squared is, mu x squared is 1. Mu z squared is 1. And mu z mu x plus mu x mu z is 0. This is on the same link. And if they're different links, then they commute. Mu z mu x, so mu z on link L and L prime is mu x L prime mu z L. So they commute on different links, and they anti-commute on the same link. Okay? And that's it. So I could write down this Hamiltonian, give you these relations, and give it to a mathematician, and tell him to figure out everything. You don't need to know anything else. This is the algebra of operators, and that's it. Now, what's going on? What is the property, what is the spectrum of this Hamiltonian with these operators? Okay? Yes? Yeah, so I'm coming to that. I'm coming to exactly that. That's the kind of thing I want to discuss. Okay? So this is what's called the Z2 gauge theory. It's not exactly solvable, but we can do perturbation theory in it. And it has two phases. There's a confining phase and a deconfined phase, which are the analog, respectively, of like Cork confinement in QCD of free electric charges in electromagnetism. It's the analog of that. And it also has a phase transition between them. And, right. Okay. So why is this a gauge? Yeah, the question was, why is this a gauge theory, for example, right? So this theory, first of all, has this gauge invariance, which I mentioned earlier, that I can change mu z ij to si mu z ij, sj, where mu x ij goes to mu x. So under this transformation, so Si and Sj are plus or minus 1. So this is just a change from mu z to minus z while you retain the x field. So if you think in terms of spins, that means you just rotate by 180 degrees about the x-axis. If you rotate a spin about the x-axis, z goes to minus z, x remains itself. So that's just a 180-degree rotation. So you perform this canonical transformation, 180-degree rotation, depending on these Si and Sj can be different at different points in space. And the Hamiltonian won't change, as I discussed this morning. So you can do this 180-degree rotation on some sites. You can do it on this side and that side and this side, and not on the other ones. It's a symmetry. So it's not like a usual symmetry where you can only rotate all the spins together. That's that's called a global symmetry. This is a local symmetry because you can do the rotation here or here or here or here or here. Okay. And this is analogous very much to, if you want to see the analogy with electromagnetism, you should think of mu zij as somehow looking at exponential I, integral from I to j of A dot dl. This is the usual electromagnetism. This is the phase factor, Aharonov-Bohm phase factor. You go from one point to the next. This is from I to j. If you go, this is the phase factor you're going to get. That's what this is. Here it's a phase. Here this is plus or minus 1. So the Z2 gauge theory is somewhat like having the Aharonov-Bohm phase factor has only two values, 0 or pi. That's it. So you just restrict your gauge field to just take two values, 0 or pi, rather than living on a circle, okay? And then you can see that this is very much like under gauge transformation. We know that, we learn here gauge transformation, A mu goes to A mu minus D mu phi. And if you put that in here, that goes to exponential ij A dot dl times e to the I phi I and e to the minus I phi j. That's the gauge transformation of the Aharonov-Bohm phase factor. And what this relationship, so now you can see that Si is e to the I phi I. So SI, and the Z2 gauge theory is the analog of e to the I phi I. And again, phi I only takes two values, 0, pi, whereas in the gauge theory it's continuous. So you can see it has exactly the same structure as electromagnetism, with the restriction that the gauge field be 0 pi. Okay. Now, what about what is mu x? What is the interpretation of mu x? Well, that's a little tricky. So the interpretation of mu x will turn out to be like an electric field, square of an electric field. But let's see how that works out when you look at some pictures in a little bit. So this is like this term is like, this you can see this term, for example, in the U1 gauge theory, it would be cosine of, A dot dl around a plaquette. It's just the cosine of the flux to the plaquette. It's a very physical thing. So that's why I call this the Maxwell term. It's just the like B squared, cosine of B through a plaquette. Okay. Okay, so that's one of the reasons this is, interesting, because it looks so similar to electromagnetism. And you can do the same story even for non-abelian gauge theory. It will all have the same structure. So let's forget about that. Now let's try to solve this on its own merits. All right, so this is I have a infinite number of symmetries. Now we know from Noether's theorem, every time you have a symmetry, you have a conservation law. So therefore, I must have an infinite number of conservation laws. So what are those conservation laws? So conservation laws are the following. So I need to find an operator which commutes with the Hamiltonian. Okay, and I want to find an infinite number of operators that commute with the Hamiltonian. That's also kind of unfamiliar to us. When we deal with Hamiltonians, there's just one or two or three, but not an infinite number. But that's the property of any gauge theory, is an infinite number of Hamiltonian operators that commute. So you can just stare at this and try to figure out what those operators are. And it's really very simple. You pick any site I here, and this is a site, there's a site J here, which is the nearest neighbor of I. Then I can define the following operator. We call it G sub I. For every site I have an operator, which is the product on J belongs to nearest neighbors of I. Of mu x times ij. So just take the product of mu x on this site I, take the mu x here, mu x here, mu x here, mu x here, on these four links. Okay? And that commutes with both terms. And why does it commute? Well, obviously it commutes because mu x commutes with itself. Okay, how does it commute with this? Well, you can see, if this plaquette, this is an actual plaquette, and if that's, if it's somewhere out here, well, no big deal, these commute. But, so you have to put it somewhere down here. So you take this plaquette some more. So I have product of mu z over here on this plaquette, and gi is the product of mu x on these 4 points. Now you notice there's a mu x here, which anti-commutes with the mu z here, because of this relation. And there's a mu x here, which anti-commutes with this mu z here. Both of them give you a minus sign, so together they give you a plus sign. Okay? So easy to show then that all the gi commutes with the Hamiltonian. Every one of them. Okay, what this is an analog of is Gauss's law in electromagnetism. You may know that in Gauss's law, which is del dot E equals 0, this is pure electromagnetism. I haven't put any charges yet. In pure electromagnetism, there's an operator that commutes with the Maxwell Hamiltonian, which is del dot E. Right. or it's really E to the I del dot E. So this, I guess I'll just leave it at that. If you try to do canonical quantization of electromagnetism, you can check that del dot E commutes with the Maxwell action, the usual quantum electrodynamics, and this is at any point in space. So here also, this is for any x del dot. There's an infinite set of conservation laws in electromagnetism, which is the del dot E. 0 at every point x. So that's not something that comes from the equation of motion. It just comes from it's a constraint on your Hilbert space. Sorry. It's just a set of infinite number of conservation laws that just comes from the commutation relations of the theory and your Hamiltonian. But since I don't want to talk about electromagnetism, forget it. It's obvious this is true here. Okay? So where's Kedar gone? He wanted me to talk about something. Yeah. All right, so this, what I've defined here is called a pure gauge theory. So no, sorry. So a pure gauge theory, or the vacuum. So we have to choose, since these commute to the Hamiltonian, we have to choose a value. I mean, so you give me the value of GI, I'll get a different Hilbert space. Okay, so I have a Hilbert space that depends on the values of GI. And also, GI is an interesting operator because its square is 1. It's a nice simplification. So the square is 1. So GI is an operator. Its only eigenvalues are plus or minus 1. So, and it commutes with the Hamiltonian. So if you want me to diagonalize the Hamiltonian, you have to tell me ahead of time what the values of GI are. Because they can take any value you want. It's like saying if I ask you the spectrum of the hydrogen atom, angular momentum commutes, so you have to tell me I want the energies of the S states, or the P states, or the D states. Here I have an infinite number of things to tell you. Okay, so what we normally say under convention is that when GI is equal to 1 everywhere, so GI equals 1, is what we call as a Z2 gauge theory. With no charges, no electric charges. So that's just the vacuum. So the vacuum of the theory is by convention declared to be the state, which is the ground state of this theory, where GI is 1. Okay, on every site, yeah. Okay, find something more? I don't know, you just have to look and stare and see if you can think of anything else. Yeah. There's no guarantee, of course. I mean, okay, so, if two things, if there may be others actually, come to think of it. If you find two conserved quantities, then the commutator is also a conserved quantity. Well, these actually all commute, so there's nothing there. That won't do. Yeah, well, okay. No one's ever mentioned any, so I don't know how to prove it. I mean, you could probably prove it. There is nothing else. Well, there's, of course, momentum and things like that, because there's translation invariance. So the total momentum commutes. And the Hamiltonian energy itself, those are always there. And so on. Okay, everyone with me? All right, so we just declare the Hilbert space, the GI is 1 everywhere. And this we're going to call actually the set of gauge invariant states. So let me also explain that. So there's a connection actually between this gauge transformation and GI. Okay. So what GI does is that it generates a gauge transformation. Because suppose I pick a site I, okay? So in other words, let me say this more carefully. GI, I should have said this earlier, generates, it's the generator of gauge transformations. Actually, this is again something very familiar. Suppose I tell you I have a Hamiltonian that's rotationally invariant. So that tells me by Noether's theorem that there's a symmetry. There's a conserved quantity, which is angular momentum. And then you know angular momentum is the generator of rotations. So here I told you the Hamiltonian gauge invariant has infinite number of symmetries. here's the operator, and that operator, therefore, is the generator of that symmetry. So we have to just check that. So here's first of all, GI commutes with all the mu x, no problem. And GI acting on mu z ij is the same. So GI acting on mu, commutator of GI with mu z, not commutator, I guess. Okay, I have to be a little careful. There's factors of pi over 2 and so on. Yeah. It's not because compute mu z with mu, you get a mu y. So you want to do something else. You want to do rotation about the x-axis, right? So what is the generator of rotations is e to the I pi times gi. Okay. E to the I pi. That's the generator of rotations. Rotation about the x-axis, probably a 2 because sigma x over 2 is the rotation. Okay, I'm doing this on my feet. You have to get all the factors of 2 right. So what I'm trying to say is that GI or this operator e to the I pi over 2 GI acting on mu z ij is the same, will give you minus mu z ij if this I is equal to that. And that means that SI is minus 1, okay? So the gauge transformation with SI is generated by e to the I pi over 2 GI. Again, you can check that. Yeah, no, that's correct. You rotate Z about the x-axis when 180 degrees. Okay. So that's now, so then that leads me to the point I was going to say, that when GI is 1, right, so since GI is the thing that operator that performs gauge transformation, if I now act on a state, so we want the state. We want the ground state, say, we want states psi such that G psi is equal to psi. Okay, I think I may have some of the notation bit screwed off here. Maybe GI minus 1. Anyway, GI minus 1 may be the thing that annihilates. No, anyway. So this means that the state, when you hit GI on it, remains the same because GI is 1. So that we say that this state is gauge invariant. Okay, so that's the Hilbert space you're going to look at, the set of gauge invariant states. Yeah, okay. Maybe that's not I may not have said this in a clear way because I should have prepared. I'm just doing it at the top of my head. All right, but let's just say here. GI equals 1 is a theory with no electric charge. Okay. So then if I make GI equals minus 1 somewhere, if I say that I am looking at a state where GI is minus 1 here, that'll be a state with an electric charge sitting there. That's analogous to taking a state where del dot E is not 0, but del dot E is equal to rho. Then the right-hand side is what the electric charge is. So here, when GI is minus 1, that means GI equals 1 for every I. And now if GI equals minus 1, that implies there's what we call an electric charge at site I. So this is a static charge. It can't move. It's just sitting there. Static electric charge at site I. All right. So now I ask the following question. I'm going to take these. So these are like very heavy static charges. They don't move. I'm going to look at the ground state energy when I have two electric charges next to each other, and I move them far apart, and ask how does the ground state energy change when I move two electric charges far. That's what I want to ask. And what you'll find is that there's a completely different answer depending on whether K is much bigger than G or the other way around, okay? So we can define the potential, so let me write this out. So let's see. Let V of I comma J equal the ground state energy, Eg, with Gi equals -1 and Gj equals -1 and all other, and all Gk, other Gk equals 1. So this is where I put two charges, one at side I and another at side J. And then I subtract out, obviously, the ground state energy with all Gk equals 1. Okay? So I pick two sides I and J, and then I put charges there. I figure out the ground state energy of the Hamiltonian. Then I remove the charges, figure out the ground state energy, look at the difference. That difference is the potential energy of the two charges. Okay? I'm allowing for arbitrary quantum fluctuations of the electromagnetic field, in this case just a Z2 gauge field. So this is a bit tricky to compute, at least in one limit, but let's compute it. It's easy to compute in the limit when G is much bigger than K. So this is what we want to compute what V of Ij is in two opposite limits. So let's look at G much bigger than K. So that's a really simple limit because I can just write down the ground state. If I just throw out the K term, when G is much bigger than K, then I have this mu x. I just want the ground state with mu x equals 1 on every side, and mu x equals 1 on a spin that's pointing in the x direction, right? Because this is just sigma x, so eigenstate is spin pointing in the x direction. And G is assumed to be positive, so that lowers the energy. So with no charges, my ground state, G, is basically, looks something like this. Every site has a spin pointing on the x, on the right, where, so mu x acting on the right is just mu x. It's the eigenvector of mu x, with eigenvalue plus 1. That's trivial enough, okay? Okay, so with no charges, this is what I do. Now let me put two charges, one here and one there. What does the ground state look like? Let me come back right here. So remember that I have to have G is equal to 1 everywhere except on 2 points, okay? So the ground state has, let me put the points here. So there's a point here, this is the side J, and say this is the side I over here. And right now I put mu x equals 1 everywhere. I want mu x equals -1 here. That means at least one of these, an odd number of these 4 should have mu x equals -1. Every time mu x equals -1, from this term I pick up energy 2g, which is huge. So I want to minimize the number of -1s. So this costs a lot of energy. Every -1 costs an energy. Okay, so clearly I don't want 3, I only want 1. I want 1 -1 over here. So this thing becomes -1. This is mu x equals -1, and +1 everywhere else. All right. Now here, I've got to have product of, there's no charge there. I've got to have product of mu x equals +1. I already have a -1, so I've got to have another one. I have no chance. I have no alternative to have another one. So where should I put it? Well, now you can see you probably want to put it here. You could put it there, but we'll see that's going to not be good. Because you just want the shortest path to go from here to here to here. If you pick anything else, it costs more energy by an energy amount 2G. So what you see is that V of ij, you can see from here right away, V of I comma j is equal to 2G times what you can call as the Manhattan distance, at least from the square lattice. You have to move only horizontally or vertically. You can't move diagonally between I and j. Okay, which is, so the farther apart they are, the more energy it's going to cost, and energy cost keeps growing and growing and growing. And if you move them horizontally, linearly with the distance between them. So that's confinement. And that's what happens to two quarks. Well, not really. If you take two quarks and pull them apart, eventually the string breaks, and in between you get two more quarks. And so you get two mesons. Here, that will also happen here once I put in charges that are dynamical. Right now the charge is static. So a G much bigger than K, this is a confining theory. Electric charges are not free to move apart. They always come in pairs, and they have strings between them. They're never free. So that's confinement. Okay, and now you can check that this is all perfectly stable. You can do a perturbation theory in K over G along the methods that Kedar has discussed in the first lecture. And basically, it may change what's called the string tension. So this 2G is the string tension. The value of the string tension may change a bit, but it will be non-zero. Okay? So, all that clear? Now, yes, yes. Yes, yeah. Yeah, correct, right. Right, because GI is -1 only at the ends. It's only, there are two charges, a charge here and charge here. There is -1, everywhere else is +1. So I put the constraint as -1 here and -1 here, and then I have no choice but to put this through. The string cannot break. If the string breaks, that means you have a charge there, by definition. Okay, I mean, maybe, yeah, there's some, the kind of system I discussed this morning, you can actually be in such a phase. But in fact, when you do antiferromagnets, quantum antiferromagnets, this is for Kedar partly, and I'll come back to this if I have time. The ground state is not GI equals 1 everywhere. The ground state is GI equals -1 everywhere. And then when you think about that state, then you find that the ground state is a valence bond solid. But okay. Here it's a unique ground state, and then you have confinement of electric charges, which is linear. So the one with the GI -1 everywhere is what's an odd Z2 gauge theory. Okay, so the trickier part is to do the other end. So we do the same thing, but now we do it for K much bigger than G. Okay. So the first thing you want to do is write down the ground state wave function. And at least in this language of the G charges, it's not so trivial, but it's not that bad. I can write it down, at least when K is practically infinite. So when K is very, very large, what do you have to pay attention to? You have to pay attention to not to mu x, but to mu z. the canonically conjugate variable. And the product of mu z around every plaquette should be 1. So if you want to make every plaquette happy, it's an obvious choice. So you can say, aha, my ground state wave function, every plaquette, I just put every link, I put every spin up. And then this is perfectly happy. This is as low as energy as you're going to get. And give you +1. And this one is very small, so don't worry about it. And you're done. So that's actually the correct answer. For many purposes, once you have enough experience with gauge theories, you just work with this. But to be completely consistent with my definition so far, and to be able to identify where the charges are, the trouble with this wave function, I want a wave function that let me call this psi tilde, because it won't be the exact range wave function. What is Gi acting on psi tilde G? It's not 1. In fact, it's nothing. It gives you a different state. So let's just see what it does. And that will also give us what we want. The actual ground state must be such that Gi acting on psi G is psi G. That's what I want. Okay? But Gi acting on psi tilde G is going to give me some other state, as we'll see. Now, one thing I'm sure of, whatever I get over here, that state has the same energy. It has to have the same energy because G commutes with H. So here, I'm finding there's a huge, and if this for any G. So in fact, I have some degeneracy in the ground state. And this is not a particularly good wave function as far as this condition is concerned. So what is Gi acting? So I have, let me, this may set the stage for what Kedar is going to do tomorrow, although you listed so many things that you probably won't get to this. Okay. So I put Gi equals +1 everywhere. So it was up, 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 up everywhere. That's psi tilde G. Okay. Then I come in, let's say on this site, and I hit Gi. So what Gi does is flips the spin on 4 sites. Okay. So these will go down. These will go down. Okay. And now this state actually is also a perfectly good state. If I take the product of sigma z around any plaquette, it's still +1. 1, 1, -1, -1. It's +1 everywhere. So this has the same energy. Okay? I'm not taking that into account. I'm taking this is perfectly happy. Okay, and then I can do it here. I can do it, keep doing it. We can do it twice here, and so on and so on and so forth. You can see there's many different things I can do. And it turns out to have a little picture of what you're doing. And the way you draw a picture in analogy with what Kedar just did, I'm going to draw a line. Let's draw a wavy line, or dashed line, across every downspin. So this configuration corresponds to a loop around this plaquette. So now I come in and say I hit, yes? No, mu x acting on up gives you down. Mu x is like the Pauli matrix, 1 in the off diagonal. So sigma x acting on up gives you down. Sigma y acting on, there's no sigma y here, sorry. Sigma x acting on down gives you up. Just a thin flip over it. So now if I, for example, I hit a Gi over here, then this will flip back, but these 3 still will flip. But now I can think of that as this loop. Okay. And I can keep doing this, and what I will see is I'm just going to get closed loops, right? So each psi tilde can be represented by a loop. So this will give me psi tilde. This was just the empty psi tilde. This psi tilde I can represent by some loop here. Okay. So now I can write down psi g. I want a state that's invariant. So what I want to do, and what does GI do? What GI is a simple operation that just either gets rid of a loop or moves a loop or something. It's an operation that takes you from one configuration loop to the other configuration loops. So if I write down my wave function, okay, then my actual wave function in this regime is sum over all closed loops. So the sum of the set of all closed loops. And then for each set of closed loops, I have a state psi tilde of C. So the sum, you give me a set of closed loops that you draw on the lattice, and I have to sum over all of them. The reason I want to sum over all of them is when I hit GI on this state, it's going to take me from one loop to another loop. So it's just going to rearrange these terms. So the sum will come back to itself. Okay? That's the idea. Okay, that's at k goes to infinity. Now, Kedar, if he gets to the toric code tomorrow, it's a very similar model, but this term is slightly different. And this sum over closed loop wave function is an exact eigenstate for all values of G. So that theory, in fact, is always in this phase, whereas doing perturbation theory in G is a bit complicated, and I'm not going to try to do it here, but it can be done. You have to compute various correlation functions on this thing with lots of closed loops on the square lattice. All right, so what about if I put two charges in the wave function? How am I going to put two charges? Well, so I have to put product of, so let me do that over here. So I want to put let me see if I'm actually doing this on my feet. I don't think I've ever done this calculation before. So here's my score lattice. So I put a charge here, and I put a charge over there. Okay. So what I want is a state. If I hit GI on this state, then I get back the same state, but with a -1. But if I hit GI anywhere else, I get back the same state with a +1, right? That's what I want to do. So if I now draw some closed loops, suppose I have some loops here. Here I have one loop that looks like this, in the same pictorial representation. Then, well, okay, so on. Can you have four? Yeah. Can you have 4 lines coming out of the same point? No, right? They're all disconnected. Kedar, remind me. Can I have? I can have another loop over here, right? I can, yeah, I can. That you can do that also. This is another loop. But let me make a loop over here, which is enclosing. So here's some loop configuration. Okay. So now I'm going to say, for the psi, the charges at I and J, I'm going to assert the following, is equal to sum over all closed loops of the same set of states, psi tilde G, which depends on the closed loop, times -1 the number of loops enclosing I and J. Okay, that's my assertion. So I'm going to take, here I took just the positive linear combination of every one of these closed loops. Every closed loop, so you give me a set of closed loops, I have a configuration of spins up and down. They're all perfectly happy because they all have no flux. The K is just, this is always +1 for every one of those terms. And now I'm going to just take the same sum, just put a phase factor in front. Okay, so why does this do the trick? So what's going to happen if I hit GI over here, then what's going to happen? Well, if I hit GI at this point, there was no loop encircling this. And when I hit GI, what's going to happen is that the loop is going to go do that. It's going to annihilate that and move this over here. So I've got another closed loop, which is encircling it. But now this closed loop in this sum comes with the opposite sign, right? Because now there's a loop. Previously, there wasn't a loop. I hit GI, now there is a loop. And in this sum, those two loops come with opposite signs. So if I hit GI on any term here, it's going to flip its sign. So GI acting on this side will flip the sign of every term in this sum. And similarly for GJ. So we're done. Okay, so this is the wave function with charges at I and J. And what we find is that this wave function has the same energy. You're perfectly free to move the charges where you want. They don't care. So here, it costs a huge amount of energy to move them. They're confined. Here, they're free because no matter where they are at large K, they have almost the same energy. They have exactly the same energy as K goes to infinity. Now you can do perturbation theory in G, and I think you find there's an energy that falls off exponentially with the distance between them. So there's some very weak attraction, but it's exponentially weak. Now if you did this for U1 gauge theory, you would get a Coulomb 1 over R. So that's the difference between discrete and a continuous gauge field. Since it's discrete, the forces are exponential in the free phase. Okay? Good? Yes. Very elegant argument, right? Yeah. Right, so the loops are running on the dual lattice. And every time a link of the loop crosses this line, you flip this thing. That's the rule, okay? So this configuration, this will be up. This will be down, 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 down. This will be up. And everything else is up. Okay, and so on. So the loop, whenever a loop hits a line, you flip this thing. And that's why when I hit GI, it either adds a loop or removes a loop, right? Because it flips all the 4 spins around the site. Okay. So now you've seen that there are 2 phases. Well, at least for K much bigger than J, we have deconfinement. The charges can move freely and it costs no energy at all. For G much bigger than K, we have confinement. The charges don't want to move. They get trapped. And so it turns out that the actual situation, and this is more difficult to prove, is that there's a phase transition in between. There's a quantum phase transition. You go from the confining phase to the deconfining. And for this particular model, this model is actually exactly dual to Ising model on the dual cubic lattice, on the dual lattice quantum Ising model. And the universality class of the phase transition is the 3D Ising model, the Wilson-Fisher fixed point in some dual language. But I'm not going to show that. Okay, what I do want to show is one other thing, is that the deconfined phase, in addition to having these electric charges, has another set of very interesting excitations, which you can think of as magnetic vortices. That's what the analog of magnetic monopoles. So, you may have heard that non-abelian gauge theories necessarily have magnetic monopoles, which no one's ever seen, but all these theories have magnetic monopole excitations. And this theory also has something which is an analog of a magnetic monopole. Okay, so that's why I call these electric charges. They're also magnetic charges, the analogs of magnetic monopoles. Okay, everyone okay with this? I'll just, all right. So now I'm still going to be looking in this regime. In fact, every state I've written down in this regime has the same energy. I'm just taking different linear combinations of them to produce electric charges, and they're totally free to move around. You can easily see now you can put 5, 6, 10 electric charges. They all have the same energy. Okay, but so let's look at something that has a higher energy, but only by a finite amount. Okay, so what are those excitations look like? Okay, so now I start. So let me start with all spins up. That I know is the lowest possible energy. It's not gauge invariant. It's not invariant at the G, but after some work, I figured out how to make it gauge invariant by summing over all closed loops. I mean, those of you who have studied quantization of gauge theories, you may have learned about the Fourier-Popov method, where you fix a gauge and then you integrate over all gauges, and that gives you the right gauge invariant partition function. That's pretty much what this is. It's sort of like that procedure. When you're summing over closed loops, you're just integrating for all possible gauges. Here it's very discrete and easy to do. You don't have to produce ghosts and horrible things like that. It's just the sum of all closed loops. Okay, so this is the lowest energy state, all spins up. Now what I want to do is actually do something with this guy. So let's say I want a state with energy, just the smallest possible excited state, which is not in this low energy subspace of free electric charges. Yeah.
Another way of writing the same state is this IG with all possible product Gi and sum over.
Yes.
All
yeah.
possible numbers.
Yeah. Well, it has to be. So it's very important that each closed loop appears once and only once. So when you're not only hitting GI once, you could be hitting it twice, three. I mean, you're also all distinct GI, but all products of different GI at every yeah. In a way, I mean, it's really crucial that every loop occurs only once and only once, and so that when you hit a single GI, it's just a rearrangement of its terms. Okay, so now I want to just hit this guy just once. Okay, so if I do this, I'm going to pay an energy cost. So if I just hit it once, everything else is up, and I hit it just once. If I hit that on this state, I flip this, and this is now an excited state. And right now I'm working the limit where G is small, right? Yeah, well, K is very big and G is small, right? Right, okay. So this costs energy cost of the state relative to the ground state is 2g, because this went from having, no, sorry, am I saying this right? I'm not saying this right. Huh? Thank you, you're right. That's why I was so confused. It's a huge energy cost. It's 2K because this plaquette is expensive, that plaquette is expensive, all of this. So again, yeah, when you do degenerate, as Kedar showed us, you have to get these zeroth order states. And this is now in the second excited set of states. First, there's the ground state manifold, which I've already discussed. Now we have some first excited state manifold, and that's at energy cost 2K because of this plaquette. Okay. So now I could have hit this anywhere. So I have these things all over the place. But now I need to do degenerate perturbation theory in G. G is a small correct. Okay. So what can G do? Well, G can come along and say flip this spin. Okay. Now when I flip this one, then this plaquette is certainly happy again. It still has energy 2K. But there's an off-diagonal matrix element of order G. So from moving these two plaquettes unhappy to these two plaquettes unhappy. So let me just put an X here for the unhappy plaquette. So hitting an G moved an X. First of all, the first time you hit G, you created two X's. Now you hit the G here, it moves one of the X. And then I can hit it again, and then it moves here. So the X now can move around freely. It'll have some dispersion that's given by the coupling G. So it becomes a particle, and this also moves around, and they're free to move. Connecting them is a string, but the string of down bonds, but it doesn't cost very much energy. In fact, it costs zero energy diagonally anyway. You can just keep moving this forward. So this X is excitation with the magnetic flux. Initially, the flux was 1. Now the flux is -1. The product of mu z around it. So that is the analog of a magnetic monopole. And this, so the deconfined phase, in addition to having free charges, electric charges, also has free magnetic charges. And these are called Wisons in this context. Because they're associated with vortices and so on and so forth. But here, that's the name given by Senthal and Fisher, and it's kind of stuck. Although they were certainly well known well before in particle theory. So these are magnetic particles, and then there's electric particles. Now, one thing I haven't discussed is how to make this guy gauge invariant. So there's no electric charges here, so I should have a state where I hit GI and get back to the same state. So I'm going to have to sum over closed loops in some complicated way. I'll let you figure out how to do that. Maybe Kedar will do that tomorrow. Wake up. Okay. All right, so finally, what I've shown you is that there's electric charges, there's magnetic charges, and they're both free in the deconfined phase. In the confined phase, the electric charges are bound, and what I won't discuss, but one can show in the confined phase, the magnetic charges are condensed. They're like post-condensed. And that's what leads to confinement. That's kind of the dual magnetic picture of confinement. Again, this is something you can show by just playing around. Ultimately, all we're doing is just perturbation theory. Very simple perturbation theory of the type this Kedar described to come up with this picture. Finally, there's one very interesting feature of this, which has to do with these -1s over here. And I don't think I can do it with my feet, since I'm not prepared myself for it. Yeah, well, it has to do with this branch cut here. Suppose I have both electric charge and a magnetic charge. And then I move the electric charge all the way around a magnetic charge. Well, imagine doing that. And what you'll find is that when the electric charge crosses this branch cut, it picks up a -1. So these electric and magnetic charges are relative semions. So that's a They're anyons. They're sort of like the fractional quantum Hall excitations, where in the fractional quantum Hall state, if you move a quasi-particle around another quasi-particle, pick up a phase factor, they're all the same type. Here you have quasi-particles of two types. You have the electric quasi-particle and the magnetic quasi-particles. And the magnetic particles are bosons, the electric particles are bosons, but if you move an electric particle around a magnetic particle, they're all right, they pick up a factor of minus. And that's part of why this is a topological phase, because of that anyonic factor, and that's what can be associated very intimately to the ground state degeneracy that I talked about this morning, and many others. Okay. All of that beautiful structure is in this very simple Hamiltonian, which has been around for a long time. I mean, the existence of two phases, confinement and deconfinement, I guess that's due to Franz Wegener was the first to point it out. But some of these more subtle aspects of topological order ground state degeneracy, they weren't appreciated until relatively recent, when people started seeing the analogy with the quantum Hall effects. All right, what time is it? Okay, I'll leave it up to you. What do you want me to do next? So, okay, I can propose something. If you want to hear it, I can talk about it. If not, we'll both be happy to call it a day. Which is, I can say a little bit about what's called the Schwinger boson. I actually start with an antiferromagnet in this large U perturbation theory that Kedar described, and then work with it and massage it and massage it. And in the end, you get a structure which is very similar to this Z2 gauge theory. I don't think I have the time to go through the whole route. There are some notes on that I wrote up recently. But that's one thing I could at least start with. Okay, since I have the notes, why don't I just flash the notes up and wave my hands a lot? Since you're all tired, I'm tired of writing on the board. And then we'll just see how long before we all fall asleep. So can I have the screen down? I'll just give you a flavor of how it works. There's a couple of pictures I want to show. That may be the... Actually, let me use that other article, now that I think of it. I'm going to have to... sorry? Yeah, no, I will do that in 1 minute. Okay, let's just... All right, so we start with this Hamiltonian. Just on the square lattice or some frustrated... So let's say the triangular lattice, where this is the simplest. Okay, so we're going to do a large N theory of this. And if you do it just right, and you follow all the rules, and you think carefully, in the end, you end up with a structure which is very similar to the Z2 gauge theory. So the statement is that there's some invariant universal structure, which is this topological field theory that describes the Z2 gauge theory. And the same topological field theory also describes this antiferromagnet under right conditions. Of course, it's very hard to predict ahead of time which topological field theory or which phase you're going to get given a certain Hamiltonian, but in the large N limit, you can work this out. All right, so what we're going to do is write the spin operator in terms of Schwinger bosons. So S dagger sigma S. I think, did Kedar introduce this? Kedar's gone. Okay. Did he introduce this? No. Yeah, it's all probably too fast. Okay, let me try it a different way. It's in the other article. I mean, this took me like 2 whole lectures when I taught this in my course, so 1.5 hours each to explain this. Let me just do it in terms of pictures. Okay. Right. So this picture here on the left, upper left, this picture here on the left is what the RVB wave function, right? It's the famous resonating valence bond wave function. Probably you've heard Bhaskaran talk about it. You take electrons on an antiferromagnet here on the square lattice, and you have them form spin singlets, okay, this way. And and so this is some configuration of spin singlet, which you call DI, and then you sum over all the configurations. So your wave function is the sum over all configuration of the singlets, which is written over here. Okay, and the sum over all configuration of singlets is somewhat analogous here to the sum over all closed loops, because if I take 2 different dimer configurations and put them over each other, that correspond to some closed loop configuration. So it's kind of analogous. So the wave function is this very infinite set of terms, here being sum over all sets of singlets and that you can form on the square lattice. This is all kind of approximate, of course. So then here's what we do. Right. But then what are the, so this thing, as I said, is the analog of this deconfined ground state. What does this state look like? Well, what this state looks like is I have these 2 free electrons, which have spin 1/2. These are called spin-ons. And now I can move them apart and pay hardly any energy cost. You can think of the orange arrows as the electric charges. The spin-ons are like the electric charges. They're free to move apart, and they're moving in the sea of these fluctuating loops, which don't do anything. They allow them to move at no energy cost. So those spin-ons are the analog of the electric charges of the Z2 gauge theory. Okay, so then the question becomes, what is the analog of a magnetic charge? All right, so the analog of a magnetic charge is the following thing. I put an X where there's a magnetic charge, and then I draw a branch cut around, starting from the X. So this is just like here, starting from the X, there was a branch cut. It doesn't cost any energy, but it flipped these spins, and this goes off to the other guy, all right? And here, what do I do? So here's the following thing. So for every dimer configuration, I had some weight. So initially, my wave function was sum over all dimers times some weight Ci. Now I want a wave function that's an excited state, which has this branch cut in it. And what this means is that if there's a dimer on this bond, Ci goes to minus Ci. So the dimer on this bond, on that particular state, it goes to minus Ci. So basically, the effect of this X and this branch cut is to change the signs of some of these Ci. Some of these Ci's go to minus Ci, depending on how many dimers they have crossing the cut. Okay? So that's precise analog of this magnetic excitation. And here you'd call this a Y zone. So it's an actual excitation in this spin system if it formed a spin liquid. Okay, and finally, the most important thing, which is really tells you this is a Z2 gauge theory. So there's a long, complicated way of doing all of this. Is you do this process where you move an electric charge or magnetic charge around an electric charge. Okay. So here's an electric, oops. Here was an electric charge and a magnetic charge with a branch cut. And you move the magnetic charge all the way around. So as it moves, you get more and more of the branch cut. Okay, and now you have this branch cut that comes back and then goes out. So now this state is not the same state as this one, even though in terms of excitation, they've come back to the same point. What it differs from is the change in the dimer on every bond coming out of this side. Okay, but that, I can get rid of that by a gauge transformation. I can just do a gauge transformation on this side. It doesn't change the wave function at all. And that gauge transformation changes the sign of the spin sitting there, or the boson sitting there, by -1. And therefore, that's where you get the -1 factor. So this feature that the magnetic charge going around the electric charge gives you a -1. A Berry phase of -1 also comes out of just thinking about these wave functions. Okay, so I'm so that's the flavor. I know I haven't explained it, but I'm really too tired to explain it. I suspect you are too tired to listen to the details. But that's the idea, and of course you can do this much more carefully with an actual calculation, which are in several of my papers. And in the end, then you can conclude that the universal structure, the nature, the quantum numbers of the excitations, the electric and magnetic charges, and the mutual statistics are identical to certain spin liquid states, which are called Z2 spin liquids for this reason, as they are for just the pure Z2 gauge theory with its excitations. And so really the whole gauge structure, it's really fundamental. It's just, you can't get rid of it. You have a topological spin liquid, you're going to have the gauge fields, because as it's kind of forced on you just from the structure of the waveform. All right, I should have been a bit better prepared on this, but that's what I have for now. Okay. So this, yeah, you may want, there are fairly explicit details in this article. Let me just at least give you the archive number. This is an article with Debanjan, my student who just graduated. So that's the archive number over there, 1605 43579. And it's with minimum of technicality, I try to just explain using pictures and a few equations, what does a spin liquid look like, and why does it look like similar to a Z2 gauge theory.